Sometimes it's easier to convert integrals into cylindrical and spherical coordinate system because it makes the calculation easier. When we're talking about cylindrical coordinate system, they basically represent the point as r, theta, and z, which is basically the polar coordinate form. R is the distance between the point and the origin in xy plane. Theta is basically the angle between the positive part of x-axis in xy plane, and z is basically the z value. When you're working with cylindrical coordinate system, x is r cosine theta, y is r sine theta, and z is equal to z. And as I mentioned before, this is basically polar coordinate system extended to this space. Another coordinate system is spherical coordinate system. In spherical coordinate system, you have a point in the space. You have three elements, rho, theta, and phi. Rho is the distance between the point and the origin in the space. The minimum value it takes is 0. Theta is the reflection of the point in xy plane. And as you can see, it's just basically have the complete rotation if you want to. But for phi, which is the angle between positive part of z-axis and the point, the maximum value it can take is pi, or 180 degrees. When you're working with spherical coordinate system, x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. And as we mentioned before, rho is x squared plus y squared plus z squared, or rho is the distance between the point and the origin in the space. Perfect. So in spherical coordinate system, we said we represent the point by rho, theta, and phi instead of x, y, and z. And we mentioned that x is rho sine phi cosine theta, and y is rho sine phi sine theta, and z is rho cosine phi. Rho squared is x squared plus y squared plus z squared. Now, if you have a triple integral in x, y, and z, we can convert that into spherical coordinate system where rho is bounded between a and b, theta is bounded between alpha and beta, phi is bounded between c and d, which is a spherical wedge. The visualization here helps us to make the calculation and find the volume element, which is rho squared sine phi d rho d theta d phi. This can be written as f of rho sine phi cosine theta. Wherever we see x, we're going to substitute that by rho sine phi cosine theta. The next variable is y, which by definition is rho sine phi sine theta. So substitute that here into the function, rho sine phi sine theta, and z by definition is rho cosine phi. So wherever you see z, just substitute that there. You get rho cosine phi. And for the volume of element that you have here, it must be equals to rho squared sine phi d rho d theta and d phi. Then you take the integral with respect to rho, the integral with respect to theta, and finally the integral with respect to phi. Okay, let us take a look at one example here. Suppose I ask you to evaluate the triple integral of x squared plus y squared plus z squared to power negative 3/2, where d is the region in the first octant between two spheres of radius 1 and 2 centered at the origin. Let's take a look at visualization here. Try to feel comfortable about this object. So z is equal to square root of 1 minus x squared minus y squared. Remember that the question says it's in the first octant, so I'm going to just focus on the positive part of z. And the second one is z equals to square root of 4 minus x squared minus y squared, which is a larger sphere. We basically want to take a look at the object between these two spheres. But again, remember that here you have the first octant. It means that everything is positive. X is positive, Y is positive, Z is positive. So you're basically looking at this object bounded between these two spheres in the first octant. X is positive, Y is positive, Z is positive. For the very first sphere, rho is 1. The second sphere is of radius 2. So rho must be equal to 2. So your rho bounded between 1 and 2. This is obvious from the object that you can see here. Now for the rest of the variables and the boundary for theta and phi. So this is our object that we are looking at. This is our D. And well, as we mentioned before, this is in the first octant. In XY plane, the rotation is from positive part of x-axis and it stops at positive part of y-axis. It doesn't go further. So your theta is bounded between 0 and pi over 2. What about your phi? Phi, by definition, is the angle between positive part of z-axis and it goes down here and stop at this point because it's on the first octant. So your phi also bounded between 0 and pi over 2. By definition, rho squared is x squared plus y squared plus z squared. And dv, the volume element, is rho squared sine phi d rho d theta d phi. Okay, let us begin, everybody. This is the triple integral of f of x, y, and z dv. So here, if you plug in rho squared into the parentheses, rho squared and a half, they get canceled out. You end up with rho to power negative 3 times rho squared, rho bounded between 1 and 2, then sine phi d phi, phi bounded between 0 and pi over 2, then d theta, theta is bounded between 0 and pi over 2 as well. But the calculation is not that difficult. If you combine rho to negative 3 and rho squared, you get rho to power negative 1. Then you take the definite integral of rho, while rho bounded between 1 and 2. Then you take the integral of sine phi d phi, y phi bounded between 0 and pi over 2. And finally, the integral of d theta, theta bounded between 0 and pi over 2. Remember that the integral of rho to power negative 1 is ln of absolute value of rho. Since rho is bounded between 1 and 2, if you do the substitution, you get ln of 2. Then you take the integral of sine phi. You calculate the integral, which is negative cosine phi. Phi is bounded between 0 and pi over 2. Then you do the calculation for d theta. You have ln of 2. The integral of d theta, theta is bounded between 0 and pi over 2, which is basically pi ln of 2 divided by 2. So the most important thing here is for us to make sure we understand the behavior of theta and phi. And again, as we mentioned before, let me change the ink color. When you're working with phi, phi starts from positive part of z-axis and go further down. And it doesn't go any further because by definition, by this example, and by definition here you have the object stop at this point, which is the angle pi over 2. The same for theta. It happens to be bounded between 0 and pi over 2 as well, because theta is in xy plane. You start at positive part of x-axis, and since it's in the first octant, you have to stop here. It doesn't go further. So your theta also bounded between 0 and pi over 2.